speaker is Hitoshi Murakami from Tohoku University. The title is The Color Jones Polynomial and the Representations of a Knot Group.
Thank you very much. Thank you for introduction and thank the organizer for inviting me. This university, Waseda University, is the university when we found that the Kasheff's invariant indeed specialization of the Color-Jones polynomial. We means Jun Murakami and I. So I was at Waseda University, and it was March 1999. I was visiting Nishi-Waseda Institute, Sweden, for a year, and Jun Murakami was also visiting there for a month. And Jun Murakami proposed me to work together, and at that time he was sure that Kasheff's invariant is specialization of the Color-Jones polynomial. And indeed it is. He said that the Kasheff's invariant is indeed the intersection of the Color-Jones polynomial and multivariable colored Alexander polynomial, so-called Otsuki, no, Akutsu-Deguchi Otsuki invariant, ADO invariant, and we work together. So anyway, it is kind of history, and yes, this talk is partly joint work with Ann Chan, University of Texas at Dallas. So this is the plan of my talk. So what is the volume conjecture? I hope everybody knows it. Let J n be the Color-Jones polynomial. Here, the capital N is the dimension of irreducible representations of SL2C, and K is a knot, and Q is a parameter, a complex parameter. So it is a Laurent polynomial depending on N. And the volume conjecture says that if we replace Q with the nth root of unity and take the absolute value, take log and divide it by N, the limit is the volume over 2I. This was first proposed by Renat Kasheff in 1996. Preprint appeared in 1996, maybe. So Jun says so. So this is the 20th anniversary of Kasheff's conjecture, and so we proved that Kasheff's conjecture is this kind of specialization of the Color-Jones polynomial, and the preprint appeared in 1999. So everything happened in last century. So quite old classical conjecture. And here in the right hand side, Tomotada Otsuki gave a lecture on Tuesday, and he assumed that K is hyperbolic, and also at the first, I think Renat Kasheff's original conjecture was for hyperbolic knots, and here I mean volume is the so-called simplicity volume. In other words, it is also called Gromov norm, which is the sum of hyperbolic volumes of hyperbolic pieces in the complement. So you may know that for any knot, its complement can be uniquely decomposed into pieces. Some of them are hyperbolic and some of them are ciphered fiber. Here I draw some pictures. So let us consider the, so this is a cable of the figured knot. So you have, so here you see the figured knot, but this knot is not the figurehead knot. It is called 2-1 cable of the figurehead knot. It goes twice along the figurehead knot. And this is not hyperbolic knot because we can find torus in the knot complement, a green torus, you see. And if we decompose the knot complement into two pieces by this torus, then we have two pieces, and one is outside of this green torus, which is the same as the figurehead knot complement. So this space is hyperbolic. But here, this one is the solid torus minus this red curve. This is not hyperbolic. This is called Seifert-Fiebert. And the volume of this knot is, by definition, just the volume of this piece, because this Seifert-Fiebert piece is something like surface cross S1. So it is very thin, so the volume is assumed to be 0. So by using this volume, the volume conjecture says that the left-hand side is equal to the volume of the knot complement. So for hyperbolic knot, as Otsuki said, that there is a famous conjecture which is a kind of generalization of the volume conjecture, saying that the asymptotic of the color zones, so asymptotically it is equivalent to, so here S0 is, I think Otsuki used just volume. So this is just complex volume, which is called Chern-Simons invariant, SL2C Chern-Simons, which is I times volume plus real Chern-Simons invariant. So if we ignore the SO3 Chern-Simons, this is just the volume, because there is I and there is I. So you see that if you take log and take the absolute value and take log and divide it by n, then you have S0 divided by 2 pi I multiplied by n. So we have just this one, which is the volume. And another thing is the tau of 0, and which is the Reidemeister torsion. And I will explain later. This Reidemeister torsion is associated with the holonomial representation. A holonomial representation gives the complete hyperbolic structure of the knot complement. Yes, and this conjecture was proved for the figurehead knot by Andersen and Hansen, and for knots up to 7 crossings by Otsuki and Yoshiyuki Yokota. I'm not sure who gave proofs. Takata-san, tadashi desu ka? It is, right? You are involved in this proof? Takata-san 入ってない。So, Otsuki Yokota and Otsuki himself. Otsuki and Otsuki Yokota.
6が大月横田、7が大月。
Oh, I see. So, Otsuki and Otsuki Yokota and Otsuki. Okay. Anyway, and Takasa-san will give a talk about 8 crossing knots tomorrow. Yes. So, anyway, this is a kind of generalized volume conjecture. So, the Carl-Jones, for a hyperbolic knot, Carl-Jones gives volume, complex volume, and the Reidemeister torsion, both associated with holonomial representation. And what happens if we are, so I write u equals 0 But what is U? So this is another generalization of the volume conjecture. So I'd like to replace 2 pi I. So recall that Kashev's conjecture is a specialization of the Carl-Jones polynomial at the nth root of unity, exponential of 2 pi I over n. So I'd like to replace 2 pi I with by using a small parameter u. So I'd like to replace 2 pi I with 2 pi I plus u, which I put with I. So u is assumed to be small parameter. And then the conjecture by Dimofte and Gukov and myself is saying that again the Carl-Jones gives the complex volume and Reidemeister torsion. But in this case, we have parameter u, which gives another representation of pi 1 to SL2C. You know, for hyperbolic knot is a knot with such that its complement possesses the unique complete hyperbolic structure, but we can perturb the complete structure slightly by using complex parameter u. So u is a parameter which gives incomplete hyperbolic structure. So rho u is a representation into SL2C, sending the meridian to e to the u over 2. Yes. Then if we are given this kind of representation, we can define the Chern-Simons invariant and the Reidemeister torsion, which I will explain soon. Oh, yes. And this conjecture is approved for the figure knot with Yokota and myself for small real u. And I hope we can use Otsuki and Yokota's method to prove this conjecture for other knots with small crossings. Now I'd like to explain what is the SL2C Chern-Simons invariant associated with the representation. Let X m be the SL2C character variety of 3-manifold M. So this is the trace of representation, the set of traces of representations. And the CS Chern-Simons invariant is defined as follows, which is a map from the character variety to C modulo integers. Given representation, irreducible representation, then we can associate a flat connection on M cross SL2C. And then Chern-Simons of this class of rho is defined to be by using this integral. And so let me see. Yes, this is so sorry. This is not so. This is just a remark. Sorry. Okay. And the definition of Reidemeister torsion is as follows. Once again, rho is a representation, and A3 minus K tilde is the universal cover of the knot complement. Then the chain complex of this universal cover is regarded as Z pi 1 module via the covering translation. And this is D algebra. The D algebra SL2C can act on this chain via adjoint action of the given representation. So this one is sorry. Yes. So we can consider the tensor product of this chain complex and the algebra SL2C. So we denote it as C star. This is a chain complex twisted by adjoint action of this representation. And our Reidemeister torsion is the torsion associated with this chain complex. So as usual, we consider its homology group and fixed basis of chain complex and boundary group and cycles, and then we can consider the base change matrix and its determinant, alternate product of the determinant of the base change matrix gives is defined to be the torsion, Reidemeister torsion. And if we consider three manifold with closed three manifold, this is well defined. But if we consider three manifold with boundary, we need to fix basis for homology group. This is kind of important in our theorem. So this torsion can be defined once we fix a basis of the homology. And the torsion appearing in this conjecture is the torsion associated with the meridian, because first homology of the twisted chain complex is one dimension. H1 is non-trivial, so we need to H1 and H0 are non-trivial. So we need to fix the basis for H0 is clear. We can fix one point, but for first homology there are some choice. So this torsion is associated with the meridian. Now we so far we consider volume conjecture for hyperbolic nodes, but next we consider non-hyperbolic nodes. In general, knot complements, as I described, if there is incompressible torus in knot complement, the geometry of knot complement it can be very complicated. But if there is no such incompressible torus, the knot is either hyperbolic or torus. So next, I like to consider torus knot, and the conjecture for consider the original case, that is Kasheff's invariant. So for the torus knot with the volume conjecture for the torus knot was proved by Kasheff and Tirkoni in 2000. I think it was the preprint appeared in 1999, before the volume conjecture. So and later Dubois and Kasheff proved this. No. I think this formula was already obtained by Tirkoni and Kasheff, and Dubois and Kasheff gave topological interpretation of these terms, SK and SK tilde. So what are they? So the K is an index for the set of all irreducible representations from the knot complement to a pi1 of the knot complement to SL2C. Here, TPQ is the torus knot of type PQ. So on standard torus, it goes P times along the longitude and Q times along the meridian. So in this case, there are many irreducible representations, and so such representations appear here. So asymptotically, the color zones split into this kind of summation, and each summand here SK0 is the once again complex volume that is SL2C Chern-Simons invariant, and tau is essentially the Reidemeister torsion associated with this irreducible representation. Once again, because in this case the first homology is one-dimensional, so we need to specify a basis, and we take the meridian. And let me see. Yes, and in this case, SK0 is purely imaginary, no, real. So this part is purely imaginary. So this is not exponential growth. So if we take absolute value and take log and divide it by n, then the limit goes to 0, which agrees with the volume conjecture saying that such a limit gives the volume, because the volume of the torus knot is 0, because the complement of a torus knot is Seifert fiber, so its hyperbolic volume is 0. I think this is the first proved volume conjecture. And what happens when u is not 0? So once again, we replace 2 pi I with 2 pi plus u, then something similar happen. But in this case, there is an extra term, which is 1 over the Alexander polynomial. So in this case, if u is not 0, we have first Alexander polynomial and some of terms coming from irreducible representations. So the range of k depends on u, but for some u, we have all the irreducible representations. And the Alexander polynomial can be regarded as the Reidemeister torsion associated with the abelian representation. So we can say that in this asymptotic, all the representations appear.
But
yes.
You cannot go continuously to u equals 0, right?
No. And yes, it is a good comment, because you see that there is 1/2, but when u is 0, we have 3/2. So there is, as Rinat mentioned, we cannot make u. We cannot replace u with 0 because one reason is that there is hyperbolic sign here, and also Alexander. This is okay. Yeah, this is okay. So if we want to recover Tilkonen and Kashaev and Dubois' result from this one, we need to take derivative with respect to u or something like that. So it is not trivial. So we need to discuss separately in the case where u is 0 and u is not 0. By the way, Garfaridis and Tande proved that for small guzai, so we talked about Xi was close to pi I, but in this case Xi is close to 0. Then they proved that the Color-Jones itself converges to 1 over the Alexander. And as I told you, the Alexander polynomial can be regarded as the Rademacher torsion associated with abelian representation of this kind. So, as I told you, in this, the right-hand side, this is abelian, and this is reducible representations. So I think it is interesting that asymptotic behavior of the Color-Jones polynomial, all representations appear in a sense. So this is how to calculate, how to prove asymptotic expansion of Color-Jones in the case of 2a plus 1 torus knot. This is very simple. We can, so for the Color-Jones, we can consider Kaufman bracket, and using linear scaling theory, it can be easily seen that the Color-Jones can be given in this formula. And when we replace t or q with exponential of Xi over n, then we can, this is the technique by Telkoni and Kashev, and we can use this kind of integral formula, and we can replace the summation with integral, this kind of integral, and C is a line passing through the origin. Then so we can see that this integral goes to 0 because this is minus, but by assumption of Xi, this goes to 0. We can ignore this, and we want to evaluate this integral by using so-called saddle point method. To do that, let me see. Yes, we make complete square. We complete the square, and so the integration is along the line passing through the origin, but the saddle point, which is yes, the saddle point is not the origin, so we need to move the contour by 2a plus 1 Xi, like this, and we need to add residues between this line and this line. And using the saddle point method, the first, this gives the the part coming from irreducible representations, and the first integral, this one, gives the Alexander polynomial. So we have this result. Yes. This is a result with Kazuhiro Hikami. Sorry. So we get the Alexander polynomial and Chan-Simons and torsion, torsion associated with irreducible representations. Now we further consider iteration of torus knot. So here I draw a picture. So we consider 2b plus 1 cable of 2a plus 1 torus knot. So this is 2a plus 1 torus knot, and inside the torus knot we consider another torus knot which is twisted 2b plus 1 times in this way. Now we can see, so that the you can see a torus along the original torus knot. So there is an incompressible torus in the knot complement. So the complement splits into two pieces, and both are Seifert fiber. So the volume is 0, and sorry, this is the Carl-Jones of this iterated torus knot, and Roland gave a formula for general. So we can iterate this operation again and again, and there is a more general, much more general formula for Carl-Jones of such iterated torus knots. And so this is a joint work with An Chang, and Liu already proved this kind of formula. So we consider the asymptotic behavior of Kasheff's invariant. Then, as before, the result split into several terms, and let me see. So the complement of the iterated torus knot is split into two pieces, and the first two summations corresponds to irreducible representations, one such that one piece is abelian and the other piece is non-abelian, and one piece is non-abelian and the other is abelian, and the last one corresponds to non-abelian representation. And once again, as in the case of torus knot, there appears torsion and Chern-Simons invariant associated with such representations. And another point is that we have three halves here, like torus knot case. And here we have power of 2 for non-abelian part. And note that in this case, the twisted homology we consider is two-dimensional. The first dimensional twisted homology has a dimension 2, so we need to fix two bases. So I don't know precise relation between dimension of twisted homology and precise relation between this power and dimension of twisted homology, but this may indicate something. And this is some. And when u is not 0, we need to replace 3 halves with half and 2 with 1, and similar summations appear. And one more, this is abelian. This corresponds to abelian representation, which is 1 over the Alexander. So for iterated torus knot, the calculation is quite similar to the case of Kasheff and Tilkonen. So the calculation is very elementary, but of course complicated. But essentially, it is a kind of undergraduate complex analysis. And so this is and the last case, this is this result is still in progress. We like to consider some cable of the figure knot, and its complement has incompressible torus, which divide the complement into hyperbolic piece and Seifert fiber piece. And in this case, due to our calculation, we have only one term. Of course, sorry. Tanre and Chan proved the original volume conjecture in this case. They indeed proved that so this is the asymptotic behavior of the color zones, and you can easily see that if we take absolute value and take log and divide by n, we have this one. So this is indeed the volume of the knot complement. So this proves the volume conjecture for the cable of the figure knot. But we, Chang and I did something more, and we found some extra sum. This may corresponds to complex Chern-Simons invariant. So this is the volume part, and this is real Chern-Simons part. And this may be Rayleigh-Meister torsion associated with some irreducible representation. And we have n squared. This corresponds to the case of iterated torus knot, where we have non-abelian representation. But unfortunately, there seems to be no such non-abelian in figure knot complement and non-abelian in cable space. So we don't know which representation corresponds to this value. So this work is still in progress, so we don't know any comments on work. So it's sorry, I started. Sorry, but I'm hungry, so I'd like to say thank you.
Any questions or comments? Lunch?
One question.
Yes.
So, if a knot is not hyperbolic, there is a maximum volume for every PSL2C representation. The volume function takes a maximum value in the character variety.
Yeah.
That maximum value can be strictly less than the ground model.
No idea. So you mean non-simple knots? Knots with
non-hyperbolic knots.
So I don't know. Even for no, I don't know. There are maybe interesting cases. All the pieces are hyperbolic, but I have no idea. Or I don't know whether such kind of good representation. I don't know either nice expression for character variety of knots with incompressible torus. Do you know any?
The volume takes a maximum value,
Yes.
and the Schreiber invariant lim sup is also finite.
Yes.
Take the lim sup is another value. Are these two equal?
Yeah. No, I don't know. And maybe calculation is practical calculation is very complicated.
Yeah.
So if we because the number of crossing is very big. The smallest one may be more than 16 or something. So it's almost impossible, even for computer calculation.
Any other comments? So let's begin.